All right, it's recording video. And let's see if it complains about audio. So that might work too. We'll see. Okay, so is iPad recording too? Okay. Yep. We're ready to go. At last. Yeah. Okay. So again, technical difficulties are plaguing us, but it should work better this time. So we have this lecture being recorded twice. So whatever recording succeeds will get posted. Okay. And I'm aware of 2 people so far that have finished homework 2. I'd rather have something that's late and more complete than not late and not very complete at all. So feel free to take some additional time within reason, because there's still the other assignments coming up that have to be done. So, okay. Does anyone have any questions about homework 2 stuff? Anybody down the coast? All right.
Yeah.
Oh.
She can't remember.
Wait, well, I have one of you.
She has a question.
So, for number 3, when we're trying to derive the air bound,
Yeah.
and that's going to come about through the definition of R?
Yeah.
The RAE, that definition?
Yes. The AE equals R, and also the formula that produces each new residual from a previous one. So those 2 things used together will allow you to come up with a relationship. So really what you want to do is find relationship between the norm of each R and the norm of the previous R. And then you can apply that repeatedly to get a relationship between RK and C, which is R0.
Okay.
Okay.
Okay, thank you.
Yep. Anything else from down there? Kilia, did you have something?
No, not right now.
Okay.
I have a question related to where you have in the, I guess in the hint on number 2, where you have RK is less than some constant to the K times C.
Yeah.
In mine, I've gotten some constant to the K plus 1. Does that matter? I mean, I guess it's kind of better in where it's faster.
Oh, that's strange. It should be K, yeah. Because you don't, like I said, I was just telling Leah, you have a relation between norm of RK plus 1 less than or equal to some constant times RK. So you just apply that repeatedly to get so that the difference in indices should match the power of that number. So yeah, so something went amiss. Okay. Anything more? Okay. Lately I've been talking about stationary iterative methods, Jacobi, Gauss-Seidel, SOR. But now we'll take a look at non-stationary iterative methods, the cooler iterative methods, in my opinion, but also more broadly used. So I'm going to spend this week just focusing on one non-stationary method in particular, the best known one, the conjugate gradient method. And then next week I will spend some time on a few other ones that are related. Okay, so this is 5.3. Okay. Conjugate gradient method is so popular we actually threw it a birthday bash because it was invented in 1952 So in 2002, they had a conference in Switzerland to honor my advisor, Gene Galdo's 70th birthday and the 50th birthday of this method. But it's that widely used. So the general form of a non-stationary method so it doesn't rely on a splitting like an m and an n like a stationary method does. We're still solving ax equals b. Each iteration is going to have this form. So a new iterate is equal to the previous iterate plus some constant, alpha k, times some vector pk, bless you. And this is called a search direction. So from your latest guess, you try to determine what is an appropriate direction to search in your n-dimensional space to try to improve on this solution. And then once you have a direction in mind, then you try to determine how far should you travel along that direction to get to your next iterate. Okay. Now, so the thing is, how do we choose a search direction? And once we have that, how do we choose this parameter alpha k? So the idea is I'll come up with a simple way to determine those that will lead to a method called steepest descent. And then we will improve upon steepest descent to get conjugate gradient. All right. Okay.
Dr. Lambers,
Yes.
are we in the part of the section, the notes that are new?
No. The new section I covered last time.
No, but didn't you say you rewrote something? Is this part of the section that you rewrote?
No.
No.
Yeah, that was last Wednesday.
Okay, thank you.
Yeah, I covered the new 5.2 last Wednesday because the old 5.2 had already been covered. Okay, yeah. So this is existing notes. Okay. Oh, so you're all set to. Okay, good. Okay, so first, as a precursor to conjugate gradient, we'll talk about the method of steepest descent. Okay. So this is only, for this week, we're going to focus on the case where A in AX equals B is a symmetric positive definite matrix. Okay. And the idea is our goal we're going to describe as minimizing this function of x. Phi of x is 1/2 x transpose ax minus b transpose x. Now, how do you minimize a function of several variables? So this is what you learn in multivariable calculus. You take the gradient of your function and you set it equals 0. Well, it turns out the gradient in this case, and I covered these differentiation rules a long time ago. I won't go through how you work those out. You just have to look at everything on an entry by entry level. But the gradient turns out to be ax minus b. And we want this to equal 0. So, in other words, solving a system of equations, that's what we really want. Solving ax equals b is equivalent to finding a minimum of its function. But the gradient may be 0 when ax equals b, but how do we know that this is a minimum? So this, again, is from multivariable calculus. In single variable calculus, you learn it's a minimum if the second derivative is positive. Well, multivariable calculus, you have that you have a critical point of a function of several variables. you have to look at the Hessian. The Hessian of phi, in this case, it's just a. Basically, you're taking the derivative of this. And you want the Hessian to be positive definite. It's already guaranteed to be symmetric. And that is positive definite. And that tells you that the critical point where the gradient is 0 actually is a minimum. Okay, so that's why we need the assumption of being symmetric positive definite to guarantee that. So now we can focus on the problem of trying to minimize this, and this gives us a way of choosing search directions and also choosing these parameters, these alpha k's, to multiply the search directions by. Because yet another thing you learn in multivariable calculus is at any particular point, what is the direction of steepest descent? So the direction of steepest descent from any given point, x naught, is minus the gradient at that point. So that would be b minus ax naught. So what we can do is we now have a way of getting useful search directions for our non-stationary method. So I will just go ahead and set each search direction pk to be equal to minus the gradient of phi at xk. But that's going to be b minus axk, which is our residual. So I'm going to refer to that as rk. So rk has the same meaning as it does in problem 3 in the homework. It's just a b minus ax. Okay. So now we have part of our non-stationary iterative method in place, but now we need the parameter to multiply it by. So we choose alpha k, and here's what we keep in mind. What are we trying to do? We're not just solving a system of equations, we're minimizing a function. So we've reduced this multi-dimensional, this n-dimensional minimization problem to a one-dimensional minimization problem. So I'm going to try to minimize phi of xk plus alpha k pk. Because now this is fixed. This is fixed. Only alpha k remains unknown. So I'm going to think of this as a function. I can call this like g of alpha k. So now I can do one-dimensional minimization. I'll take its derivative, set it equal to 0, and what do I get? So g prime of alpha k equals 0 when alpha k, it turns out to be its rk transpose rk over rk transpose ark. All right. So I get this by carrying out the differentiation of this using a definition of phi I gave in the previous board. I've carried out the actual differentiation in the notes. So you can check this out. That's on page 110. for all the gory details there. But that's just quantity of this expression that we got, RK transpose RK over RK transpose ARK. How come we never need to worry about dividing by 0? What? Because it's symmetric positive definite. By definition, when symmetric assuming that RK is non-zero, which it's going to be because we have not yet converged, this denominator is going to be positive. So what does it tell us about alpha k as a whole? So what about the numerator? What do we know about that? Yeah, that is also positive because that is it's a 2 norm squared of a non-zero vector. So therefore, the whole thing is going to be positive, which you'd expect because why would it be crazy for alpha k to be negative? What? Yeah, because you're already following the direction of steepest descent. So if you follow that direction using a positive alpha k, you're actually descending. So your function value with negative alpha k would actually increase. Okay, so we expect a positive alpha k, and sure enough, we get one. So now we have all the information we need. So between this choice of pk here and this alpha k, we have all the ingredients for this algorithm of steepest descent. So we can choose an initial guess. If you don't know what to choose a zero vector. So now we get your search direction this way by computing a residual. Compute this expression to figure out how far to go along that direction. So I'll just quickly write down the algorithm. So if we wanted to write code for this is what we would follow. Okay. Oh. Skype just made a noise. Not sure what that means. Oh. It means somebody sent me a message. Okay. Never mind. As you can imagine, I'm a little freaked out about something going wrong. Okay. So steepest descent algorithm. So go ahead and choose your initial iterate x naught, which might as well be 0 unless you have some compelling reason to choose something different, like you might already know of an approximate solution. And then you just iterate. Okay. So you get your search direction. So that's going to be b minus axk. Well, this is the definition of the residual. However, the more practical formula for it would be, let's see, actually, I'll address that point later. So alpha k is pk transpose pk over pk transpose apk. And then xk plus 1 is xk plus alpha k pk. And Now, what you can do at this point is somewhere in here, you can check for convergence. So the loop that I've just written will compute all of your iterates that you need. But for instance, you can check, like, what if the residual is sufficiently small? Then you can stop. Or if alpha k is sufficiently small, again, you can stop. Or alpha k times pk. So you have some criterion for determining whether the loop should stop when the iterates appear to converge to your satisfaction. Now, one thing to keep in mind is if I were to write this b minus axk as follows, b minus a xk is x k minus 1 plus alpha k minus 1 pk minus 1. But that's the same as by distributing, I get r k minus 1. Actually, this notation, pk minus 1 minus alpha k minus 1 a. Okay. Yeah. So, let's see. Actually, yeah, that'll work. Now, what's happening here is this came up during iterative refinement. This formula is better to use from a floating point arithmetic standpoint than this one because these vectors individually are both going to 0. So it's okay to subtract them, whereas these vectors are definitely not going to 0 individually, but their difference will. Okay, but that's just a relatively minor technical point here. Because this method, it turns out, on one hand, you can tell from a definition of alpha k, this method is guaranteed to make progress towards a solution every single iteration. However, it turns out that it doesn't work so well in practice. And actually, if I was thinking ahead, I would have had a MATLAB demo on hand, because I do have one. Actually, I could see about posting it on the site. So what this demo involves, I'll just describe what happens, is I'm just solving a 2x2 system with two different symmetric positive definite matrices. So in one case, it converges fairly quickly. So I just choose the initial guess of 0, bing, bing, it just takes a few steps, and it's practically there. In another example, that's still 2x2, the convergence happens painfully slow. In fact, it just keeps slowing down. You feel like time's about to stop. And the reason why is very important, and it'll give us some insight into how to improve on this to eventually arrive at conjugate gradient. Okay, so I'll try to draw two different scenarios. Suppose A is well conditioned. So that means that the condition number of A, I'll use a 2 norm here for concreteness, which is the 2 norm of A has a 2 norm of A inverse, is not very large. So condition number is always greater than or equal to 1. So suppose it's reasonably close to 1. Then the graph of phi it's going to be a nice n-dimensional bowl, if you will. And at the minimum of the bowl is your exact solution x. So wherever you choose your initial guess, it will descend rather quickly. But what you will notice, if you were to, and my MATLAB demo shows this, each direction is perpendicular to the previous one. So one thing you can always, it can actually be proven that each search direction is orthogonal to the previous search direction. So their dot product is going to be 0. So here I think it works well where you have a nice steep bowl for your graph of phi. So really it's a bowl in n+1 dimensions. But what about the ill-conditioned case? So the condition number is much greater than 1. So in that situation, the graph of phi is it's closer to a gravy boat. The level curves of phi are these really elongated hyperellipsoids. So here's your minimum, that is your exact solution x. And let's suppose your initial guess x naught is out here. Convergence will still happen, but what ends up happening is you get this zigzag pattern. Because you still have this orthogonality property, but it takes these zigzagging steps that are all very small. And in fact, they seem to keep getting smaller. So the problem is, it's nice that your current direction is completely independent of previous direction, but steepest descent has no memory beyond that. So this direction, while independent of one right before it, could be going over old ground again. In fact, that's definitely what happens in 2 dimensions. You only have 2 directions you can choose, so it just keeps repeating them. So it would be nice if each direction could be orthogonal in some way to all previous search directions. That would greatly accelerate convergence. So steepest descent is not really viable. I mean, you can prove certain nice properties about it, that it will converge, but this kind of slow convergence, totally unacceptable, especially for such a small system. It should be able to converge in 2 iterations, just like nothing. So we want to try to speed this up somehow. We want to give the method some memory. And it has directions that are independent of all previous directions tried. Okay, so that's where we're going to fix steepest descent. Okay. Now, the problem is, it is not practical to make all the search directions orthogonal or perpendicular. That would be the ideal situation. We're not going to be able to do that. It's not something of a practical, computational standpoint to make that happen. Because what you could do is, as you compute a new search direction, you could force it to be orthogonal using like a Gram-Schmidt-like procedure. But that's very time-consuming. We don't want to expend a lot of effort per iteration. So we're not going to do this. However, what we can do is make all the residuals orthogonal to each other. And it turns out that's going to be good enough for our purpose. Okay. Now, so our backup goal is we make all the residuals that we ever compute during the iteration we'll make those orthogonal. Okay. So what we're going to do is in order to make this happen, because keep in mind, each xk is a linear combination of all the previous search directions. If you look at the general form of a non-stationary method, that's exactly what happens. So what we'll pose as orthogonality in the form of our solution. So xk is going to be, now I'm going to impose an assumption here just for convenience. We'll just go ahead and assume that our initial guess is always going to be a zero vector. And if it's not, then all this can be adapted, but this will just simplify things. So each solution, xk, is going to be this matrix qk, which is n by k, times some vector yk. So yk is just a vector of coefficients for a linear combination. And qk, we will require to have orthonormal columns. And that's what happens when qk transpose qk is identity. Okay, so what this says is the dot product of two different columns is 0. The dot product of a column of itself is 1, so it's a unit vector. Okay. Now, I'm going to assume, and I can do this without loss of generality, that the right-hand side vector b is just going to have a 2 norm of 1. And you can always normalize it if it's not. And the reason why I'm doing that is I'm going to prescribe that the first column of qk so q1 is just going to be b. So I'm going to use b as my very first search direction, which makes sense because that's a direction of steepest descent when your initial guess is 0. Okay. So in fact, what I'm going to do is these q's, I'm going to keep building them up from one another. So each new q is going to be the previous q. So the old columns we keep around, and then we just add on a new one. And therefore, q1 is just going to be b. Right. So the question now becomes, now that we've determined q1, how are we going to determine q2, q3, and so on? How are we going to build this up so that this is going to be a matrix of orthonormal columns, so each new q has to be orthogonal to the previous ones, but also gives us good progress towards solving ax equals b. Okay. If we take a look at how each residual is defined, because it's obvious residuals we want to make orthogonal. So rk is b minus axk, but now I'll fill in what all these things are. So b is the first column of qk, and then xk is qk yk. All right. So what this tells us is each residual is a vector that's contained in the span. So it's a linear combination of columns in QK and all the columns of AQK. So whatever vectors we get from QK itself and then multiplying all of them by A, our residual is going to be some linear combination of these. So what we might as well do is define each new column so that what we're doing is we keep growing this subspace by multiplying by A. So what we'll do is, actually I should use a fresh board for this. Well, from an efficiency standpoint, whatever columns I already have in here, I could go ahead and multiply them all by A. And then my residual is a linear combination of all of these. But if I have K columns here and K more columns here that are linearly independent, I now have 2K columns to search to find my residual. And that space is going to keep doubling in size. I don't want that. That's a large space to hunt for a residual in. What I'd rather do is make sure that multiplying by A is only going to give, multiplying these vectors by A is only going to give me one new vector, one newly linearly independent vector. So the way I can do that is the following. So I can choose, so based on knowing what subspace the residual is in, I'm going to choose the columns of QK to be an orthonormal basis of what is called a Krylov subspace. I want to get this out of the way quickly because I labored under this delusion for more years than I want to admit. Krylov, not Krylov. So it's a Krylov subspace, and the notation I use is you start with a vector B, that B in this case it generates the subspace, and your matrix A that helps you generate it, and then you specify the dimension K. And it is the span of B, AB, A squared B, and so on, all the way up to A to the K minus 1 B. So you have a K-dimensional subspace. So this is the dimension. This is your starting vector. And what you do is you take your starting vector, just keep multiplying by A. So in other words, what you'll get is the space, the subspace of all polynomials of A in A up to degree K minus 1 times B. So this makes sense because suppose we take all these columns that give us the columns of QK, and now we want QK plus 1. Well, if we go ahead and multiply all these columns by A, then we just get these guys all over again. And then we get one new column. So that way it keeps our subspace as small as possible. Okay. Now I'm going to require that all the residuals are orthogonal. And what that gives me is B minus AXK. If I take this and multiply by QK transpose, this is taking a dot product of this residual, because this is RK, with all the previous residuals. Okay. Now, if I work out what that is, So that's QK transpose B minus QK transpose A. And then XK, I'm going to include the form of that. That's QK YK. And this has to be the 0 vector. Now, B is the first column of QK. So the first column transpose this is going to be 1. All other columns transpose this, dot product, is going to be 0. So this is going to be just E1, the first column of identity. And then this, I'm going to call this TK. It is a K by K matrix. And then we have this vector YK. So this has to be 0. Okay. So now I know what YK is supposed to be. I can just go ahead and solve this system. So I can go ahead and solve TK YK is equal to E1 because we have a square invertible system. And it's small in size. A is n by n, but this is going to be k by k. Now, yes, the size of that system keeps increasing from iteration to iteration, but generally A is a very large matrix to begin with, whereas B's are tiny and just they stay small for quite a while. Okay. One thing I can also mention about TK. Let's see. Since it's defined to be QK transpose AQK, because of its definition, it is symmetric. Also, you can verify, because A is symmetric positive definite, TK is also symmetric positive definite. It actually turns out to be tridiagonal, although that's not something that can easily be seen from anything I've done up here. But it's quite convenient for solving that kind of a system. Okay. I actually intend to show that on the next page. So, okay. So at least now we have a way of guaranteeing that all the residuals are going to be orthogonal to one another. So now we have some independence of our search directions. Okay. Now,
So we're going on time here. Actually, I better check how many pages I'm supposed to get to.
not just today, but also Wednesday. Okay, so. Okay. Yeah, they'll be fine. Okay, so that means I still have time to do the super ugly stuff that I have on this page.
Yay.
I know. That's what's so lovable about this class. Okay. Hold on. All right, so the columns of QK are defined as follows. So each QK is a polynomial of degree j minus 1 in A multiplied by B. Okay. Now, these are called orthogonal polynomials. And in fact, they're even orthonormal, but in what sense? Because you don't really think of just vectors being orthogonal or orthonormal. What about these polynomials? So I'm going to define an inner product of these polynomials, and it's one that's quite natural given our context. It says B transpose Pi of A times Pj of A. So I can actually take any functions, not just polynomials, and define their inner product in this manner, as long as I can apply that function to this matrix. Note that I would normally have a transpose here. In fact, I can go ahead and put one in here. It's not necessary because A is symmetric. And this is, by saying these are orthogonal, they're equal to 0 if I is not equal to j. And they have to be orthonormal, so the inner product is 1 if they are equal. Okay, so that's my inner product of these functions, these polynomials. Okay, now it turns out that any orthogonal polynomials one very nice property about them is that they satisfy what's called a three-term recurrence relation. Okay. And it has this form, that each new polynomial in a sequence, starting from P0, P1, etc., is a combination, or can be obtained from a previous two. All right. What I'll do in this case is I'm going to define my first polynomial, which is of degree 0. I'll just define it to be 1. And that works because what I would have here is B transpose times 1 times B. B is a unit vector, so it's equal to 1 as we need it to be. Also, I'm going to define P sub minus 1 to be 0, just so that this recurrence relation is valid even when j is equal to 1. So that's not really part of our sequence. Okay, so any sequence of orthogonal polynomials satisfies this. This can actually be proven using Gram-Schmidt orthogonalization. When I taught 415, I actually proved it in there. Actually, I prove it whenever Gram-Schmidt comes up. But unfortunately, I don't have time now. I guess you've seen it twice. Okay. Okay. Now, these constants that I haven't defined yet, alpha j and beta j, these are called recursion coefficients. So any different sets of alphas and betas lead to a different sequence of orthogonal polynomials. They're chosen so as to make sure these polynomials actually are orthogonal in the sense that you define orthogonality. So it turns out that requiring these p's to be orthogonal, is what we can do is I can take this recurrence relation, take the inner product of both sides with pk, pi or pk, for instance, and certain terms will drop out, and that's what gives me formulas for the alphas and betas. So the formulas I get are alpha j is inner product of pj minus 1, lambda pj minus 1, and then the beta j squared turns out to be, well, I have one formula here in the notes, but a better formula, which actually I think is proved elsewhere in these notes. Yeah, it is actually. It turns out that the betas are always positive, so I can write this as a perfect square. Okay. So now we have these coefficients. Also, if I apply this three-term recurrence relation repeatedly, so starting from j equals 1 and then continuing, and then so now I have several equations, each coming from a single instance of this recurrence relation, I can, and also if I multiply, well, if instead of lambda, I fill in a, the recurrence relation still holds, and if I multiply both sides on the right by b, then I get this nice relationship between all of the q's. Because it's these q's I need to be able to compute. Okay, so from recurrence relation, so I'll just write down what I just described. I have beta j, pj of a, b is equal to a minus alpha j times identity, pj minus 1 of a times b, minus beta j minus 1, pj minus 2 of a times b. But this right here, that's qj plus 1. And then I have here a minus alpha j times identity. This right here is qj, and this gives me qj minus 1 coming from here. Because that's how I defined the q's earlier. Okay. Now, I can go ahead and rearrange this. So I'll put aqj on the left side, and then everything else goes on the right side. So I have j minus 1, qj minus 1, plus alpha j qj, plus beta j qj plus 1. Now, it turns out that I can rewrite this. This is true for j equals 1 and so on. If I put all these together for different values of j, I get a q k. So I'll use this for j equals 1, 2, up to k. So I get AQK is equal to QK TK plus beta K vector QK plus 1 EK transpose. So this applied K times gives us this. Because what's happening here is we're taking a linear combination of the columns of a matrix QK. So when you're taking, so what we're having is actually matrix multiplication, or TK, which is the same TK that I defined earlier. Now I can tell you what it is. So it's a tridiagonal matrix, symmetric. It has all the alphas on the diagonal and all the betas above and below, thus making it symmetric. All upper entries are 0. Okay. Now, this other term here, EK transpose, this is an outer product, like from homework 1. So what this does is this is a matrix that is all zeros except the last column, the kth column, is equal to QK plus 1. Because what happens is all of these terms here are included in this, except when j is equal to k, I got this orphan k plus 1 sitting out here, so I lump it in here. All right. Now, the other thing is, when I look at the residual, I can go back to this equation again, because now what I can do is I can multiply both sides of this by the vector yk, and what I get is aqkyk is equal to qk tkyk plus beta k qk plus 1 ek transpose yk. Now, tkyk, that is equal to E1, because I characterize the yk vector that way. Qk E1, so this whole thing, is just equal to B, because the first column of qk is B. And qkyk, that is my solution, my iterate, xk. So now all I got to do is, if I rearrange this, my residual after k steps is b minus a xk. Is this going to be equal to minus this last term? So minus bk qk plus 1 times the scalar yk, because ek transpose yk, that's a dot product. It's just going to pick off the last component of this vector yk, which is this, let's see, I'm going to call this ykk to be a little clearer. So I'm going to say that yk is y1k, y2k, and so on down to ykk. So that's what we have down here. Okay. So now what I can finally do is take all these pieces I've described in gory detail and fashion them into an algorithm that will produce more effective iterates for ax equals b than steepest descent did. Okay. So our algorithm is as follows. So to start off with, I'll set k equals 0. My initial residual will just be b. My first, so Q0, for convenience, will be the 0 vector. And this came from something I said earlier, because p minus 1 is defined to be the 0 polynomial. And my initial iterate, my initial guess will be the 0 vector. Okay. So, as long as I have not converged, I'll do the following. So I need beta k. Now I gave a formula for beta k earlier, and that was dot product of pk minus 1 with itself. But it turns out how I can actually compute that in a practical way, that's the same as B transpose pk minus 1 of a squared times b, but that's the same as, this would be squared. So this would be the same as QK transpose QK, but that is the 2 norm of QK squared. Actually, no. I can use RK here, since that's how I started it. So these are the unnormalized residuals. So, in other words, my real step, my algorithm is beta k is equal to the 2 norm of RK. So this is what we actually do. Next, I define my normalized residuals. So I just go ahead and normalize. And then I'm going to bump up my iteration count. And then I'm going to, for convenience, apply A to my latest normalized residual. And then alpha k, I have a formula for that too. So the formula I gave was pk minus 1 lambda pk minus 1. But that is the same as okay. RK transpose ARK. I just got myself into a notational quagmire. Yeah, because these are polynomials of lambda. This is the inner product of the function lambda pk minus 1 of lambda. But when you compute that inner product, you fill in A, wherever you have lambda. So if you look at the previous notation, it'll make sense. What? All right. Now my real problem here is these polynomials, these pk minus 1s, I forgot to specify when they're normalized and when they're not. Okay. Based on what I gave earlier, it should be QK transpose AQK, and that actually is the correct formula. Transpose, but AQK is VK, so I'll just use that. So this is what we actually compute here. This is what we actually compute here to get the betas. But the problem I have is no problem with this line. The problem I have is up here. What I really need is these are okay. So that is technically wrong because those polynomials are not supposed to be normalized. The ones that you use for your betas. But this is right, so let's go with that. Okay. So all right, I'll deal with that later. It's corrected on my other notes. So now I need to get my new unnormalized residual using the recurrence relation, which is taking what I have in the previous board. Okay, so that gives me my latest unnormalized residual, which then I'll normalize at the next step. But now the last thing I have to do is compute my new solution. Xk is beta naught, and then we have Qk Tk inverse E1. So this is my vector Yk that I defined earlier. Now, of course, I'm not really going to compute the inverse. I'm going to solve a system. I'm just describing what expression we need to compute. However we actually compute it is a separate thing. But we would actually use well, this is a symmetric tridiagonal matrix. You could always use Cholesky to compute this part of it, yk. But this is a form of solution I specified at the beginning, that xk is a linear combination of these normalized residuals that are now all orthogonal to each other. Okay, so this whole algorithm is known as Lanczos iteration. Okay. Now, Lanczos iteration actually serves many purposes when applied to a symmetric positive definite matrix. It can be used to solve systems of equations like this. It can be used to compute the extremal eigenvalues of A, because the matrix TK that you're getting, that's where you're storing all your alphas and betas, its extremal eigenvalues are good approximations of the smallest, so extremal meaning smallest and largest eigenvalues of A. So those are the only eigenvalues you want, is a good way to get them. And I've actually tried this, it works quite well. And so Lanczos iteration is a fundamental algorithm in many different contexts. This is just one of the most often used to solve systems of equations. All right. However, one difficulty with this is this last step here. We're solving a system of equations, and we're recomputing the vector yk from scratch every single time. So unfortunately, what we have here is this is not really in the same form that we normally expect for a non-stationary iterative method, where from our previous iterate, we choose a search direction, choose a parameter alpha k to multiply by, and then go to our next iterate. It'd be nice if we had a natural way to compute xk from xk minus 1 by choosing some search direction and going with it, and we don't have it here. We can get that, and that is actually what is going to lead to the conjugate gradient method, and that is what I'm going to look at on Wednesday. I believe you guys have suffered enough for now. But at least we have a foundation for conjugate gradient. We just need to deal with these manipulations to try to get it into this form that would actually be much more efficient than solving these larger and larger systems every time. Because at some point, this method is really going to slow down, and we don't want that. We need something in this form. So it's not just for appearance's sake. It really is for efficiency that we need to fix this. And that's what we'll look at. That's what we'll look at on Wednesday.
But that's only necessarily when you're trying to solve a system, right?
Yeah, for something like extremal eigenvalues.
We just need that TK.
Yeah, of course, TK is getting larger and larger too. So,
Okay.
yeah. But for eigenvalues, there's not much of a way around that. I guess you could apply Lanczos to Lanczos. Okay. So, till then, and let's hope that one of these recordings actually worked. If it did, we'll see you on YouTube.